So we've already spent some time talking about electric fields. So let's take a moment to contrast the difference between a magnetic field and an electric field. This can get confusing because they both involve an electron. Now, an electric field exists as a result of the charge that the particles have. They exist as a monopole. So what we mean by that is you either have a particle that's positively charged, in which case you're attracting, or you have a negative charge, you're being attracted. A particle can't be both. It's positive or negative. That's what we mean by a monopole. Whereas a magnetic field occurs in a wire when electrons start to move. So then we create a north and south end. Now this is a dipole because every magnetic material has to have both a north end and a south end. And north and south always attract towards one another. So now we draw these field lines on here to represent the magnetic field. And they occur as a result of electron spin. So what basically happens is if you have a normal material, you might have one electron with a spin this way, an electron spin this way, and so on. Now in this particular case, the atoms themselves might be magnetic, but overall it's not really measurable because the arrows sort of cancel themselves out. We have a stronger magnet when the electrons spin are aligned in one direction. This is known as the main theory of magnets. If you want more details on this, check out the other videos on the review from grade 11 stuff. Now, grade 11, we specifically dealt with the left-hand rule. In grade 12, we're going to deal with both the left-hand rule and the right-hand rule. Well, what's the difference between these two things? When we talk about the left-hand rule, this is referring to electron flow, like we have in our wires. We need to deal with the right-hand rule in grade 12 because we might be talking about colliding two protons, for example. In that case, positive charge moves by the rules of a convention flow. So instead of going from negative to positive, it goes positive to negative. Now, if we've got a straight conductor, our thumb points towards the electric field and the fingers curl in the magnetic field direction. So for example, if I have a wire, negative end here, positive end here, the electricity is going to flow this way. Now, if it flows this way, our magnetic field will point in this direction. And you can do this at home because you can look at your own hand. Your thumb will be pointing to the right, and if you're looking at your palm, you see your fingers are curling up. If we were to use the right-hand rule, well, yet again, it's the opposite. We're looking, yet again, negative to positive. We're looking at the direction of conventional flow. So in this particular case, we use our right hand. We point in the direction of conventional flow, and yet again, you'll see if you look at your fingers, they'll still curling upwards. Now the reality is straight conductors aren't very good for creating magnets because they require a lot of current, and current is dangerous to work with. So what we end up doing is we end up curling conductive materials around themselves to increase the magnetic field. We call these coiled conductors. Now the idea here is the same, but it's reversed. So in this particular case, yet again, we'll go from negative to positive. In this particular case, our fingers are the things that curl in the direction of electron flow. So we can see, since we're going from negative to positive, that our fingers should be curling up. So if we're looking at our palm, and we have our hand orientated with our left hand, with the fingers pointing up, we can see that our thumb is pointing to the right, which is by definition magnetic north. And if there's a north, well then there's a south end. And yet again, the magnetic fields will move around in a clockwise manner.